this talk, it's interesting for me because it's for Ethereum developers, and I don't develop myself dApps usually, but I work on design and the smart platform. I design at RSK, and I work in a daily basis to improve the platform and make sure that developers have the best possible platform to build upon. Okay, so RSK on the outside looks very similar to Ethereum. It has the same programming interfaces. You can use Truffle, the same development tools, but essentially it's a chain that is compatible with Ethereum, but internally it's very different from Ethereum in the data structures it uses, in the trade-off it makes, and also in the goals in the long run, in the long term. So in this talk, I'm going to talk about mostly about the internals, and also about the perception of the RSK blockchain for different audiences. So first, I will tackle how users will what are the main differences and similarities of the RSK blockchain and the Ethereum blockchain from the perspective of the user. Then I'm going to talk about from the perspective of the application developer, the dApp developers, and then for the perspective of core developers that want to know what's going on inside of an RSK full node. So that's my idea for this talk. So what about the users? So first, you have to know certain key differences from RSK to any other blockchain in existence. First, it's Bitcoin native. So the native assets of RSK is Bitcoin. And you get Bitcoin by using the PowPeg, which is a bridge that connects Bitcoin with RSK. And this bridge is not any kind of federated bridge. It's much stronger than the typical federated bridge, because each one of the functionaries of the RSK Federation is having an HSM, a hardware security model, and this hardware security model has a secure element which is tamper-proof, and each one of these models run like client, an RSK-like client, a specific type of like client which is called SPV node that follows hash rate, that it cannot be easily cheated. So the functionaries, they don't have access to their multi-sig private keys. They only have to run this security model and make sure that it's online, but they don't have access to Bitcoin funds. So it's a very advanced type of federation. Another key difference is that we are using the Bitcoin mining network to secure RSK. So it is secure by proof of work in the same sense Ethereum is secure by proof of work, but in practice, it means that it brings all this hashing power, all this existing infrastructure into RSK seamlessly. And the most important thing for Ethereum developers is it has almost full compatibility with Ethereum. So you will find it very easy to start working with RSK. So first of all, we love Bitcoin and we love Ethereum. So we are in a very, very, I would say, strange position in this ecosystem that we love the Ethereum technology because we have taken most of the Ethereum technology. And we also love Bitcoins. We are mainly Bitcoiners, and we think that in the long run, Bitcoin has a main role in this decentralized economy. So that's the reason we built RSK on top of Bitcoin. So the first thing that a user will get from perceive from RSK, it is the different average block intervals. In the case of Ethereum, it's 14 seconds. In the case of RSK, it's 33 seconds. But this is not really a huge difference, because in the past, Ethereum has moved from 14 seconds to 30 seconds, depending on the stage of the time bomb, the proof of work time bomb. And in case of RSK, the RSK miners, the Bitcoin miners, they have the possibility to reduce the average block interval up to 15 seconds. So we may see in the future that this number goes down if the miners decide to. The other thing that an end user will perceive from RSK is that it has much lower transaction fees. Of course, this is due to the congestion that happens in Ethereum right now, and we don't know what will happen in RSK. We have our own scaling strategy, but this is the current status of transaction fees. So this is a graph taken yesterday, and the RSK price for a simple value transfer transaction was about 1.8 cents, and Ethereum, it was between 20 cents and almost $1. So the difference can be quite huge, like from 10 times to 50 times, but also RSK fees are now currently much stable than Ethereum fees for obvious reasons. The other thing that the user might need to know, generally it doesn't need to know, because most wallets are seamlessly integrated into RSK and other networks, is this key configuration things like the chain ID, the different hierarchical deterministic key duration path for hardware wallets, and obviously the address of some public nodes if you are not running your own node. And also you have to know that the addresses in RSK have a different checksum, so that you won't mistakenly use an RSK address in Ethereum and vice versa. So what about the ecosystem of decentralized applications? And I'm going to take as an example the DeFi ecosystem because it's the one that I'm most interested in. And you see that in Ethereum, it's very large. It has flourished. You have many choices for each of the protocols, like lending or oracling or payments. And in the case of RSK, this ecosystem is bootstrapping right now. So the number of choices you have is shorter, smaller, but yet you have many choices to do. For instance, you have many oracling options, you have lending possibilities, you have, of course, stable coins that you can use in RSK, and those stable coins are collateralized fully in Bitcoin for instance, with money project called Money on Chain, and so you will see that the DeFi ecosystem is also growing fast. Of course, it's not as large as in Ethereum right now. Another interesting thing you will see from the ecosystem is that you have these two bridges that connect to Ethereum and to Bitcoin. So you can use the POPEC to transfer value back and forth Bitcoin, and you can also use the existing federated peg to transfer tokens back and forth Ethereum. So you can create contracts that use this functionality. And we have also created a decentralized peg with Ethereum, but it's not currently in production, but it's the next step that we are building. Okay, so what about developers? What about you? The final objective of RSK is that programming RSK is as simple as porting your Ethereum application. And currently, mostly is. You use the same tools. You have Solidity, you have Web3, the EVM, Truffle, Ganache, most of the Remix. So most of the tools that you already use, you will be able to easily use in RSK. So porting, it's generally very easy. Today, and we will have several workshops that will be given by Solange, the developer, one of the development advocates of RSK, about how to use Truffle boxes for very simply launch an environment where you can test your applications on RSK. And at the final part of this talk, I will give the word to her to explain a little more about how this works. So about the infrastructure, you have the same infrastructure service you have in Ethereum. You have your Explorer, you have a gas station to know about gas prices, stats where you can know more about the status of the network. You have the RSK testnet, which is connected to the Bitcoin testnet. So you can actually use the testnet to test the peg and send test Bitcoins into the RSK testnet and use that feature, which is also interesting. And now the thing that I'm most interested, the thing that I work every day, and so the node internals. And this is where things start to differ from Ethereum to RSK. So first about consensus. RSK has not a federated consensus. It has a consensus based on proof of work the same way as Ethereum. And in case of Ethereum, you have a specific variant of Nakamoto consensus that it's used by Ethereum. You have the block subsidy, so you have some kind of inflation. You also pay additional ethers. You have to mint additional ethers to pay for uncle blocks, and this is related to reducing to making this more fair and reducing competition and increasing collaboration between miners. And Ethereum pays immediate rewards to miners, and of course we know that Ethereum is planning to move to proof of stake. RSK is based on proof of work, and it's based on merge mine proof of work, which means that it's reusing about 50% of the hash rate of Bitcoin to secure RSK. And the plan for RSK is to keep using the Bitcoin proof of work. It uses a Ghost for weighting the uncle blocks as the Ghost paper specifies. It doesn't have a block subsidy because, of course, it's a side chain. It cannot create new Bitcoins. So it has some different different design choices related to not having a subsidy. It has a reward smoothing system where there is a shared mining account where each block reward goes to this account, and then each miner takes 10% of this account. So it's a much more cooperative game between miners than the pure competition you see in Bitcoin to create the next block. So in case of two miners create sibling blocks, the reward is split evenly between them. And also, it has a long maturity of the rewards. You have to wait 4,000 blocks to get the mining rewards. What this means in practice? It means that the security you get from the Bitcoin miners is huge, right? So this is some data taken from Crypto51.app website. Where they compute in a daily basis what amount of money would be needed to invest in. It wouldn't be electricity to try to reverse 1 hour of blocks. And in the case of Ethereum, it's about $250,000. And currently in RSK, well, this is yesterday values, it's about $388,000, assuming 50% of Bitcoin hash rate, which it usually oscillates between 45 and 70% of the Bitcoin hash rate. So you will see that the current security of both blockchains is almost the same. It's a little bit more in the RSK side, but it's comparable. You get approximately the same level of security of both blockchains. So these diagrams show the complexities of the different proof of work evaluation. How do you check the proof of work of each of the blockchains? So it's kind of, I'm not going to explain each step, but the main difference is that Ethereum 80 hash proof of work tried to be ASIC resistant or ASIC unfriendly. It didn't, it failed on the run on that, but it carries this data set that is about 4 gigabytes in size that you need to compute the proof of work. And in the case of RSK, you have to perform several hashes to get from the RSK block hash to the Bitcoin proof of work, but you don't need additional memory. And these have many implications in the kind of protocols and the kinds of solutions you can implement that can consume the blockchain. Okay, so first of all, in the case of Ethereum, you have very short proof of work. Like you only have to show the nonce, and then that's enough. But then there are some use cases that get very difficult. For instance, the ideal light client is one that follows hash rate, and you can do this very optimally or efficiently using a protocol which is called Fly Client. But Fly Client requires you sample blocks from the blockchain at random points, and you evaluate the proof of work of those blocks. And this is very expensive in Ethereum because you have to pre-calculate this huge data set for each of these blocks. So it's not very light client friendly, Ethereum currently. For the same reason, it's very difficult to implement a decentralized bridge that can understand Ethereum consensus. And you have to perform several tricks or use fraud proofs or some other more complex protocols to get to the same kind of security. You will never get the same kind of security because of the censorship resistant problems, but you move towards that goal. And we had to face this when we created the decentralized peg. In the case of RSK, the proofs are a little longer, so it's about 500 bytes, because you have this Merkle proof that proves the inclusion of the Bitcoin Coinbase transaction in the Bitcoin header. But it's not much, because it's about the same amount of bytes it takes for storing the header itself. But it allows you to create light clients that follow hash rate, and also it allows you to create decentralized bridges. So that's one of the properties of RSK proof of work. Now I'm going to switch to some other angles regarding what do we do in the RSK community regarding the EVM compatibility. In the past, we have analyzed each one of the Ethereum improvement proposals, and most of them we have merged into RSK. So the new opcodes, the new functionality, real interesting stuff that happens in Ethereum is generally very quickly integrated into RSK. What is different in RSK? So those changes in Ethereum that are, I would say, that may be harmful for the platform, but Ethereum has no choice of taking that path. One example is AP 161 that Ethereum had to do to clean the state of the blockchain after a spam attack on accounts with zero balance, and that RSK didn't need to. Another important EIP we did not implement, it's EIP 150, in particular, the reduction, the locking of gas in each call, because we think that in the long term, it can bring many problems to the platform, and particularly to Ethereum 2.0. So I think this should need to be reevaluated in Ethereum. And also, we have taken different stance on the proposals to reprise the opcodes that do I/O, and we don't need to copy those to implement those EIPs, because we have a different strategy in the long term, which is implementing storage rent. So if I have time, I will talk more about what storage rent is and how it is implemented in RSK, or how it will be implemented in the next hard fork of RSK. So let's talk about this 1/64 call gas reduction or locking. This was required in Ethereum because in the early version of Solidity, the compiler didn't warn if you used the send or the call opcode and you didn't check the return code. So there was an attack where you could force a smart contract to fail silently without the contract actually knowing about that, by calling the contract with a very deep stack field of calls, right? So Ethereum solved this problem. It probably thought it was a good reason. It solved some other problems, but it also brings some problems to the platform. So each time you ask a guest node to compute the gas estimation for the transaction, so the gas limit for the transaction, it has to perform a binary search from the maximum amount of gas in the block up to 0 to try to find the amount of gas that makes the transaction not fail, because it's very difficult to predict with a single call, because you have these gas logs in each call frame, right? And we think that this is not very good design in the long run, and I think that Ethereum 2.0 should reevaluate this, because if you have a stateful client, then you really want to be able to outsource gas estimation, because you don't have the full state, without requiring a huge work from your peer. Like I don't know how Infura is now handling this, but if it is doing the binary search, it's very, very inefficient on doing so. Happily, Ganache has implemented something called an exactimator, which allows you to get the exact amount of gas consumed by a transaction in a single call. But this requires instrumenting the EVM code, and I don't think it's a clean solution in the long run to make all these changes to the EVM only to be able to estimate gas better. In the case of RSK, we have programmed our very simple gas exactimator where it requires a single call, but we have limited the depth of cost to 400 for other reasons. There are some compilers, some languages will fill the stack if it goes into too deep. So we have limited to 400. So what about all these ideas to reprise the opcodes that do I/O? Some of them we have implemented, but most of them we are not moving forward with them because we have this plan, the community plan, to implement storage rent. The code is ready, so we are waiting for the next or one of the following hard forks to be able to merge this. And it's very interesting because it brings storage rent to the cell level. So imagine you have an ERC20 contract that has balances for millions of users. Then if you move your tokens, you don't have to pay storage rent for all the remaining users. You just will have to pay storage rent for the cells that store your own balance and your counterpart, the receiving address balance. So it's very, very flexible, and so it doesn't have many of the problems of previous storage rent proposals. One of the things that Ethereum contracts used to do very often a couple of years ago when transaction fees were a little lower was lotteries. So many contracts use the block hash to obtain some kind of random numbers or some entropy to derive some lottery prices. And there were many contracts that were malicious and just were scam, but there were some other contracts that really tried to use block hash as a means to get random numbers. Well, the actual security you get by using block hash is very, very little. In the case of Ethereum, it's about $1,000 is the cost for a miner to withhold the block and try to manipulate the outcome. And in the case of RSK, you don't even have $1,000 of guarantee. So you should never use block hash as a lottery, at least not for a single number. Maybe if you are choosing 1,000 numbers, it can be used, but not for a single number. The good news is that you have access to this oracle that contains all the Bitcoin blocks from a smart contract. So you could use the Bitcoin block hash as a means to derive some entropy for random numbers. And the cost of manipulating this, it's about $130,000 currently. So you get a little more security from that. If you want to do the same in Ethereum right now, you will probably need a third-party oracle such as a Chainlink BDF. I'm not sure if it's active today, but it will be one possibility. So what about precompiles? Well, Ethereum has 9 predefined precompiles, and currently RSK implements 8 of them, and the missing one is being implemented in the next hard fork. But you also have some other precompiles that can be useful for you if you are creating some very complex contracts or interesting ideas. One of the contracts is, of course, the bridge, which allows you to send money directly to Bitcoin addresses. You just talk with the bridge, and you can inform that Bitcoin transaction has happened, a pegging transaction has happened in Bitcoin, and pay do the pegging in RSK, or the opposite. You can send Bitcoins to the Bitcoin network. We have the Remask precompile, which is used internally to distribute the payments for miners. We have another precompile, which is called HD wallets, that allows you to do very efficient Bitcoin token offerings like crowdfunds that you want to be able to accept payment directly to the Bitcoin blockchain. And so you can use this contract to facilitate that. And then you have the block header precompile that allows you to query the headers of the last 4,000 blocks, which is for some applications where you have to prove that a transaction happened or prove that a receipt has been it's there in the blockchain, a transaction receipt. Then this is very useful. But because currently in Ethereum you can only access 256 block headers using the block hash opcode. So moving to some other internals, the block header. If you look at the RSK block header, you'll see that the first 13 fields are similar to Ethereum, but then you have some specific fields that are only in RSK. You have the field that it shows you amount of fees paid in that block. Then you have the minimum gas price, and this is something RSK has since the launch, since the beginning, which allows the network to know what is the minimum gas price that the miners are willing to accept, and this helps wallets to get a much more accurate value for the users. And it's somehow connected with the base fee of AIP 1559. While it's a much simpler mechanism, it's still you get somehow a similar result, which is a more deterministic measure of the transaction cost in the network. Then you have the uncle count, and then you have a very interesting field which is called the UMM root. This field allows you to merge mine together with RSK other blockchains or even RSK sidechains and get proof of work for them directly from smart contracts. So by using smart contracts, you can manage to provide proof of work to other blockchains. And then you have three fields that are the merge mining proof. Okay, so I have very little time, so I'm gonna go faster through this. This is one of the most interesting things that I like from RSK compared to Ethereum, is that the inner data structure that holds the state is a binary trie. From launch, it has been a binary trie. So the whole trie structure is much simple. In the case of Ethereum, it's a radix 16 trie with 3 kinds of nodes. And also, because it's radix 16, it's inefficient for stateless client. And this is in the case of RSK, it's much more efficient. And it also stores together with each node the children size. So each node stores the amount of data that it's contained in their children. So if you are going to download the state, you get an idea of the percentage of the whole state that you have downloaded, because you know the amount of data that is still pending to be downloaded. It also stores the value hash, value length, and the value itself. But most importantly, the Ethereum trie, it's split between two tries at 2 levels. First, you have the account trie, where you have the account state, and the account state have this storage root that maps to a different trie, one per contract, that stores the whole storage. And in case of RSK, it's a single trie. So this storage of a contract is stored, it's plugged in the same, these are child nodes of the state, of the account state in the trie. And by having a single trie, it makes all the state handling much easier and much uniform. Like if you want to implement a new type of garbage collector, then it will be very easy to implement in the case of RSK. Then there are some minor differences about how the keys are mapped into the trie. I would say that the main difference here is that the RSK trie maps not only a randomized prefix to have this data structure randomized and not being subject to DOS attacks, but it also stores the full original keys, the account address and the cell address. So by navigating, by scanning this trie, you can reconstruct the whole dictionary. You don't need a separate dictionary for the mapping from keys to addresses. So I've run out of time, just in time. I hope that all the data that I have collected for you, it's helpful to understand. There's many other differences, but are not so important as the ones that I mentioned. And now I'm going to give the microphone to Solange, which is a developer advocate in RSK, and she will explain things that are maybe more of immediate relevance to you if you want to start coding RSK right now. So thank you very much. And I don't think there's time for questions, but I'm ready to take any. Thank you.
Wow. Thank you, Sergio. Your talk was amazing. Even for me, I learned a lot with you. And I only would like to say that now we are officially launching our truffle boxes that was in the Sergio screen. And I will do a workshop later. So join me later to create your first DApp using RSK, using the truffle boxes. And it's for beginners, and it's a really hands-on session. So you create your DApp in your computer, and it's not only watching. So come with me, and we have a lot of truffle box. We have 6 truffle box. One of them it's basic. All 3 of them are using different front ends, and we have a box to create a token in 5 minutes. It's only unbox and publish. Your token is already done, and I will show you our version of the best uh, truffle box that I seen before. That is Pet Shop truffle box, but we did the plant box, and you know the plant box today. So see you later, guys.